Ladies and gentlemen, just before we start another picture just in front of the stage with the background of the logo of the conference, please, if you don't mind, try to squeeze.
Okay, just we can start. Ladies and gentlemen, it's my great honor to organize, open, and welcome the distinguished guests who attend the 5th International Conference on Environmental Geotechnology, Recycled Waste Materials, and Sustainable Engineering. The main subject of the conference strongly refers to the current global challenges related to the depletion of raw materials, climate change issues, promotion of renewable energy sources, focusing on sustainable engineering, implementing the goals of sustainable development and circular economy. The idea of organizing the conference is an outcome of cooperation between the University of Illinois Chicago and the Indian National Institute of Technology Jalandhar, personally inspired by Professor Krishna Reddy. The second group at this conference after Poles are the guests from India. So tomorrow morning we start the day with an Indian session. Welcome. I would like to underline that since beginning, my friend Professor Krishna Reddy has been involving me in the scientific committee and then motivated to organize the 5th series of this conference in Warsaw. Thank you, Krishna. The theme of our conference is also part of Technical Committee TC215, activities on environmental geotechnics within International Society for Soil Mechanics and Geotechnical Engineering. This is the reason why one of the keynote lectures is given by Professor Andrea Dominiani from Politecnico di Torino, the chairman of this technical committee. Thank you, Andrea, for your presence and promoting our event and supervise the committee. The third, our conference was organized in 2022 in Izmir, where one of the keynote lectures was given by the newly elected president of the International Society for Soil Mechanics and Geotechnical Engineering, Dr. Mark Ballou. Just in Izmir, I had the opportunity to meet Mark and invite him to Warsaw. Today, Mark is present here and will give a presentation on ISSMGE activities and a memory of Professor Michele Jamiolkowski, former president of this society, who 10 years ago, together with Professor Wolski, were honored just on this hall with the title of Doctor Honoris Causa of Warsaw University of Life Sciences. These professors were also my personal mentors in my professional and scientific career. Mark, thank you for accepting the invitation. We are looking forward to your lecture, which has a special meaning to Polish geotechnical scientists. Okay. Today at the conference, we are also honored to host Professor Leslie Lelouis, an outstanding expert in the field of soil remediation, and Vice President of International Society for Soil Mechanics and Geotechnical Engineering for Europe. Professor Lelouis will present the keynote lecture at the end of this session. Thank you very much for accepting the invitation and for your presence. It is my pleasure to announce that one of the main lecturers today is also Professor Katarzyna Zabielska-Adamska, President of Polish Geotechnical Committee. Your presence provides that the awareness of environmental issues become of great importance among Polish geotechnical engineering. Thank you for being with us today. I also would like to highlight the presence of one more person, Professor Devendra Narayan Singh, from the Indian Institute of Technology, Bombay, editor-in-chief of the Environmental Geotechnics Journal, published in London by the Institution of Civil Engineers. Thank you for coming and for the fruitful cooperation with your research team and we had so far. I would like to take this opportunity and warmly welcome the authorities of the Warsaw University of Life Sciences, Rector Professor Michał Zasada, Vice Rector for International Cooperation, Professor Marta Mendel, the Chancellor of the University, Dr. Władysław Skarżyński. I would like to thank the university's authorities for their strong support in promotion of technical and geoenvironmental science in the research and education at our university. Thank you for being with us today. Furthermore, I would like to express my sincere gratitude to all of our distinguished guests, keynote speakers, researchers, and all participants whose contributions and presence with enrich coming discussions. Your knowledge and experiences are invaluable in shaping the debate on environmental sustainability challenges. Finally, I would like to thank all the colleagues who work hard to make this conference happen. Their efforts I highly appreciate. Thank you, and I wish you that this conference atmosphere will be pleasant and motivating experience. Thank you. Please, Rector, for a few words for participants.
Good morning. Welcome to the Warsaw University of Life Sciences. Welcome to Warsaw and welcome to Poland. I'm really very happy that this kind of very important and needed event, such as this conference, is held here in Warsaw at my university. I'm always happy to see groups of scientists and students coming to our university, especially when these groups are related to what our university is. The name of the university, the Warsaw University of Life Sciences, doesn't reflect the Polish name, and maybe you don't know that the Polish name is the Superior School of Rural Household. So basically, our roots are in rural areas. Our roots are in agriculture, horticulture, and forestry. However, we are here to hold a conference, and I have notes here on environmental geotechnology, recycled materials, and sustainable engineering. And basically, the only word that reflects directly the name of the university is environment and nothing else. But this is what Warsaw University of Life Sciences is about. This is not about just agriculture. This is not about just horticulture, but we are about environment. We are about sustainability. We are about circular economy. We are to discuss and solve problems related to biodiversity management, to climate change, to waste management. So this is why I'm really, really happy to have you here. I'm really thankful to the International Society for Soil Mechanics and Geotechnical Engineering. I learned this name just a second ago, that you decided to hold this 5th conference here in Poland for the first time. And I am pretty much sure that this nice crowd coming from several countries, especially from the United States, from India, from Turkey and other places in the world, that this is going to be a good time to exchange knowledge, experience, and to discuss these topics not only you are interested in, but we are interested in and the society is interested in. So I wish you good stay in Poland, pleasant time at the Warsaw University of Life Sciences, and I congratulate Professor Koda and the Institute of Civil Engineering for organizing this event. Thank you very much.
Ladies and gentlemen, dear guests, dear friends, welcome at Warsaw University of Life Sciences at the first International Conference on Environmental Geotechnology, Recycle Waste Material and Sustainable Engineering. As Professor Koda said, there is a history behind this conference, and I have a few pictures. This is the first, which was held in Jalandhar in India, 2018. The second one, which was in Chicago, USA, 2019, then there was a short break because of the COVID. And again, it started in Izmir, in Turkey, 2022. Last year, it was in India, in Jalandhar. And today, we are all here at Warsaw University. And behind every event, there are people. And I would like to talk a little bit about those of them. Here are the chairs of our conference, Professor Krishna Reddy, hello, and Professor Agni Kotri, who is today not with us because of personal reasons. Our organizing committee, it's Professor Koda, hello, and Alexandra Jakimiuk as a secretary, and the scientific committee, it's me and Associate Professor Anna Podlasek. As you can see on the picture on the top, the whole history started last year. We had the opportunity, 4 of us, to go to Jalandhar to get some inspiration, some information, and some knowledge about how to organize the conference. And of course, we have a special guest, Professor Koda mentioned already, which is Rector of Warsaw University of Life Sciences, Professor Zasada. We have Dr. Mark Ballows. We have Professor Lalui, and of course, Professor Krishna Reddy. I'm very happy to introduce our keynote speakers, which is Professor Reddy from United States and Professor Lalui from Switzerland, Professor Dominiani from Italy, Professor Singh from India, Professor Kamesele from Spain, Professor Zabielska-Adamska from Poland, Professor Paleologos, hello, me, Dr. Wetzlaw from Germany, and Professor Rao from India. We are very excited about your keynote speakers, about your keynote lectures. Briefly about the themes, it's solid waste and circular economy, very up-to-date topic, sustainable geoinfrastructure, environmental geotechnics and climate change, geotechnique for renewable energy, and geoenvironmental pollution control. I would like to thank and show our collaborating institution and patrons, which you can see on the slide. And of course, our sponsors, thank you very much. Thank you for your support. And at the very end, I would like to thank our team. Actually, again, as you can see on the picture, we started the preparation last year in Jalandhar, and we finished yesterday. So I hope you will enjoy our conference. I hope you will enjoy Warsaw University of Life Sciences. I hope you will enjoy Poland. And I'm pretty sure that this conference will open the door for a new collaboration, for a new project, for our sustainable future. Thank you very much and enjoy.
So good morning, everyone. I am one of the conference co-chairs for this conference, and I want to welcome you all for this conference. And also, I want to give you a brief background about this conference series. So July 4th, today is July 4th, is a special holiday in US. So I want to wish all my US friends here and US friends in US happy 4th of July and a happy Independence Day. So I want to welcome every one of you for this conference. And also, especially, I want to thank Professor Koda. I have known him for more than 10, 15 years now. We meet all the time at conferences outside, but it's a very happy occasion to meet him at his own university this time. And so I also want to thank organizing and scientific committee members. They worked really hard to make the program really good. And I want to thank the team that has done a lot of wonderful work in organizing this conference. I want to thank the administration. Without their support, nothing is possible. So I really want to thank Warsaw University of Life Sciences for allowing this conference to be organized here. And of course, thanks to sponsors, partners, and collaborating institutions and patrons. And thanks to all authors who contributed their papers. Of course, without them, there is no conference. Presenters, reviewers, session chairs, and attendees. And I underlined reviewers because those who have written papers, those who have gotten comments, they know how well the reviews were done. The reviews were even much tougher than typical journal papers. Some of the papers have gone through reviews of 5 times or 6 times. So that shows the dedication of all the reviewers and authors doing a great job in writing their papers. So excited about starting this conference. Just a very brief background about this conference series. So this conference series was the brainchild of Professor Arvind Agnihotri in NIT Jalandhar in India. So he invited me to co-chair this conference, and I've known him for many years through different collaborations. So we organized the first conference in 2018, and it was a great success. And after that, because of the relevance of the topic, and it got interest, and it became a conference series now. And we have been organizing this one almost every year. And Professor Agnihotri wanted to be here, but he could not be here due to some personal issue. So I want to say there are so many conferences. What is unique about this conference? So it is all about emerging and impactful technical areas that you don't see the extensive coverage in other conferences, environmental geotechnologies, recycled waste materials, and sustainable engineering. And this conference emphasizes, not siloed approach, taking a broader and interdisciplinary approach. So you see attendees having a different types of background, not just a geotechnical background. And also it facilitates the international professional networking opportunities. I hope, like past attendees agree that, they were able to make new friends from different parts of the world. And also this conference promotes participation of the students and young professionals, and also create cultural exchange opportunities, and avoid bureaucracy, and give complete freedom to the conference organizers. Whoever organizes the conference, they have no restrictions whatsoever in terms of how they want to organize the conference. And also, these days conferences are very expensive, but we want to make sure that the conference is affordable to attendees. So these pictures were shown by Magdalena already. So this is the first conference in 2018. And after the conference, we had 3 edited proceedings with all the papers Scopus indexed. And this is the second conference, and we had 2 short courses and field trips. And we had 2 edited proceedings. Again, all the papers included in these were Scopus indexed. Third conference, and this is the 1 book that came out of this one. And this is the 4th conference. Last year it was held. 2 edited proceeding books are already published, 2 more in the in print. And I want to thank Swati. She is here attending the conference for her full support she's from Springer, and she's in charge of all these proceedings to be able to publish on time. So we are all excited. We are here in Warsaw. So I know, we are able to see Warsaw, and also, very nice to be on this university, because we have seen this university name on papers many times, a lot of papers published by excellent researchers here, but it's good to be on campus. And as you see, we have social events and networking opportunities, and we all going to experience Warsaw and Poland culture, and we will be having very good post-conference Springer proceedings. So I just want to announce what we are going to do in the future. So next conference is going to be held in University of Vigo, June 15th to 17th. Professor Claudio Camisella is the conference chair. He's going to show you later on a call for papers, and also he's going to give a presentation in the closing ceremony about why you should attend this conference. So hopefully he will do a good marketing job so that you are convinced to go there, not just only for technical content, but all the fun stuff that going to happen at the conference. And after that, we're going to go back to India. Professor Solanki is going to organize the conference in Surat in India. And of course, he organized many conferences, and he does extremely very good job in organizing the conferences. The future conferences, there is a lot of interest in attending the future conferences, so there is no shortage of people wanting to organize this conference. So there are a lot of nice places all around, including one location, Hawaii, that is being considered also. So after the conference, attendees get connected through various ways. So we have this webinar series and YouTube channel, and we have a LinkedIn group, we have an email listserv, we have also a WhatsApp group. So there are many ways that these attendees get connected throughout the year. So I will send this presentation through our WhatsApp group, so you will have all these links so that you can use it later on. So thanks again for attending this conference. Let's enrich our technical knowledge and make new friends at this conference. And by the way, just use this hashtag if you put any photos or anything on the social media. And this is the Photo Circle app. It's already many people are using it, and nice to share some of the photos that you have with other attendees. So with that one, thank you very much again for attending this conference, and let's have fun. Thank you so much.
Hello, everyone. Yeah, that's me, Mark Belluz. I'm so happy and honored to be here today, especially in Poland. It's a dear country to me. This is truly international conference. I see friends from all around the world, even from a small country where I come from Lebanon. Hi, Daniel. Friends from Europe, friends from USA. Well done, Professor Koda and the organizing team. Very well done. Zéro faute, on dit en français. Today, as president of ISSMGE, I will tell you more about this society, and then we'll probably introduce the more technical presentations afterwards. Yeah, this is working. Pointer working. Yes. So ISSMGE, or the International Society for Soil Mechanics and Geotechnical Engineering, is the oldest and largest society representing geotechnical engineering worldwide. It was founded by the father of modern geotechnics, Carl Terzaghi, in 1936. Since then, we have about 90 country members, including Poland, thank God. And I am president number 18. Today I will mention president number 11, Professor Michele Jamlokowski, because he is special to Poland. He has Polish origins, and he was a giant in the field. When he died, I wrote these notes to him. Today is one of the saddest days of my life. It's so difficult to express what I'm feeling deep inside. When I was elected president, my inaugural speech was about you, my friend. Everywhere I go around the world, people talk about how smart you are as a scientist and how nice as a person. Please join me with 1 minute of applause for Professor Jamlokowski. We will miss you very much. Thank you. We will miss you very much, myself, the board, and all of you colleagues in the International Geotech family. We say thank you for all what you did, and we will see you soon. Professor Jamlokowski was really special. I met him the first time in Moscow at a conference, and I had my son. My son was 12 years old. He said, "Dad, take me with you to Russia, because there they have pirated video games, and I want to collect as many as I can." I said, "Okay, come with me." But during the Geotech dinner, my son was next to me, shy, sitting, not talking, and to my right, Professor Jamlokowski and I were drinking vodka. I cannot say it loud, but... And then he told me, "Your son is quiet and shy." I said, "Yes, well, he's 12 years old." He slid backwards his chair, turned around, and kneeled down, hugging my son for like 15 minutes, talking to him, and my son changed totally. He started talking with everyone. So Professor Jamlokowski is not only a genius in geotech, but he's a magician with people. So that's why he is special. And I'm very happy that I was given the opportunity to talk about him today. He received, and I will talk about this, the Elam Medal, the International Lifetime Achievement Medal. Unfortunately, he died one day before he knew that he won the medal. So here the picture in Rome, I was giving the medal with Professor Manassero and Professor Rampello. I was giving the medal for his daughter and his grandson, whose name is also Michele. So that was a special moment for me also. This was in Rome last year. So this is about Jamlokowski, and I learned that he was given a special doctoral degree from this university, which is very good. I will keep on going, tell you more about ISSMGE. The structure, you can see it on our website, issmge.org, is the council with the 90 country members, and the executive board with the president, 6 vice presidents, and we are lucky today to have Professor Lalui, the vice president representing Europe, with us. So we are 2 from this group today. And this will stay for another 4 years, so for another 2 years, because we were elected in May of 2022. This is the board, and will be with us until Vienna, the biggest conference, the international conference, where I hope all of you will be there joining us. Also, we have 6 board-level committees helping the board and 3 projects ongoing. I'm not going to go in details with these, but I will cover mainly the working horse, the technical Oversight Committee by mentioning that we have about 40 subspecialties, and many of you are active members in those technical committees, and I see chairs of some of them. So these are subspecialties of geotechnical engineering. For the students, I don't see many young students here, maybe next time, but I encourage you to apply for the ISSMGE Foundation that will support you attend conferences worldwide. Also, I'd like to mention the Bright Spark Lecture. Next time you have a conference, you should consider having young Bright Spark lecturers. They get awarded, and so far I gave, I think, 34 or more awards, 36, to students, researchers around the world that are doing a great job. And I think many of them related to geoenvironmental geotechnics. Always we thank the corporate associates, the companies supporting the society. We have about 40 of them. My goal is to make them 400. Please visit the ISSMGE Virtual University. We have hundreds of webinars, lectures, all for free open access. Also our library, online library with the International Journal for Case Histories, hundreds of journals in the journal, hundreds of papers in that journal, and thousands of free papers in proceedings, all open access with the ISSMGE library. If you don't have an account with GeoWorld, please register. mygeoworld.com is like the Facebook of geotechnical engineering, and I like the feature of GeoMap. I discovered recently that my neighbor is a geotechnical engineer. You can zoom in, zoom in, zoom in. You have like 35,000 members on the world map. What's new at ISSMGE? So the board, since we were elected since May, we did a lot of work, and I'm going to show you what we achieved so far in 2 years. Quickly, if you open the website, you will see that I started the IITT talks, where I bring together renowned engineers with young engineers from around the world to cover specific topics. And we're trying to cover all 40 technical committees. So young engineers, male, female, from around the world, different geography, different background, some from the industry, some from academia, come together to discuss in 1 hour, 2 hours, one topic of geotechnical engineering. So far, we did 19 lectures. It's gaining popularity. And if you like to participate, please let me know. Another thing, we introduced the iZone, Idea Zone, where you can give us your ideas and we study them and try to implement them directly from the website. We exchange logo and websites with all country members. And we introduced the events in a geographic presentation. So now, if you live in a country, you want to see if your neighboring country has an event, you can view that. It's easy for me to organize my travel trips. But you can also see the list in chronological order. Like here, you can see the one we are at now in Warsaw, and the one at the bottom in Vienna, where all of you should be there. And this is where I will no longer be president 2 years from now. The pin, you can see the pin here on yes, as a board. So the board members of ISSMGE are recognized now by the new pin. One of my dream achievements as president, and maybe you can help me here, is starting Geoengineers Without Borders. It's at the image of Médecins Sans Frontières. So anywhere there is a disaster, we send volunteers, experts, or just volunteers to help with the reconnaissance. And we are now registered at the Office of the United Nations reduction of risk reduction, disaster risk reduction office. And recently, there were floods in Brazil and a big landslide in New Guinea, and we had volunteers go there. Fernando Marino from Brazil went there and had with his team preparing a report as a mission from GeoWeb. And in New Guinea, Professor or Dr. Juan Kupek was there on the same mission. He was on national TV. So we are starting this, and I'm very, very pleased to announce it. And if you like to be volunteers, please contact Professor Pierre Delage. You can find his contacts on the website to join GeoWeb. Another achievement, the new ILAM, or International Lifetime Achievement Medal. We started last year. Every year we give 2 medals. And as I mentioned, the first winner was Professor Jamlokowski, who unfortunately did not know because he died 1 day before he won. And here giving the medal to his daughter and his grandson in Rome. I will give soon the other medal to Professor Haripoulos at the conference in Sydney for transportation geotechnics coming soon. We are selecting the 2024 winners. We have 15 candidates for this year, but I will not talk about them now. A special medal was given to Professor Neil Taylor, who served as Secretary General for ISSMGE for 24 years. And now we have a new Secretary General, Dr. Andrew McNamara. Another thing we achieved in the last 2 years, we created 2 videos. I don't know if the organizers can show one of them maybe later. We will talk about it. Nice videos for encouraging more members, like country member societies, and more members are corporate associates. Very nice bulletin. You can see it now. We launched the new bulletin. I don't know if some of you saw it. It's like an e-magazine you can flip with the finger. It has pop-up photos. It has interactive videos incorporated. Very nice new bulletin for ISSMGE. President's activities since May 2022. In 2 years, I toured literally the world 3 times, attended 164 events in 33 different countries. So this is country number 33. That's why some of you do not recognize me. I became old in 2 years. But I really am doing it with passion, fully dedicated for this profession. President's message, quickly. Since I'm not presenting any technical lecture, but I like to give you my opinion, especially for the young engineers. Never ever forget the units. As a forensic geotechnics, 50% of the failures are because of bad units. Imagine in America we still use feet and pounds. What can I say? 1 milliliter or 10 milliliters of antibiotics can save your children's life. But if you remove the M, you can kill an elephant with 10 liters of antibiotics. So be very careful with the units. That's one message. And it's not in geotechnical engineering only. In November 10, 1999, NASA sent the first orbiter to take photos of Mars. But that $125 million machine disappeared. And as you see at the bottom, everyone was amazed we didn't catch the mistake between pounds and newtons in the software input. Imagine. There is another story with Canadian flight, I think 197, that they filled brand new Boeing 747. They filled it, the technician filled it in pounds, but it was designed for metric. And the flight pilot had to land plane without gasoline because he ran out of gasoline. Also, never use intuition, always judgment. Take this example. If I take a rope and throw it around the earth, this is the red line, and I make this rope only 6 meters longer, so from here to the flowers, and I ask you how high will it go above the ground? Many would jump using intuition by saying negligible, but if you do the simple math, you will see that it will rise 1 meter. So 6 meters along the perimeter will rise the rope 1 meter. Another intuition, if you take a piece of paper and fold it 50 times, how thick will it be? 10 centimeters, 1 meter. It can reach beyond the moon, actually. So these tricks show us that intuition is bad in engineering. Always use calculation and then judgment. Another thing I like to talk about is principle I teach my students, SOLGE. Before you answer any engineering problem, get the data. Once you get the data, soil, the loads, the geometry, and very important, the history, especially if you're checking a failure. Always visit the site. That's my recommendation. And then study, study, and study what's happening, the mode of failure, what theory to apply. Don't jump on the software directly. And this is where you get the strong triangle of safety, cost, and functionality. Anybody can build a bridge, but it will either collapse or cost very much if it's not an engineer doing it. So in summary, run sophisticated thinking before running Plaxis. Sorry, Daniel, but so use as many data possible and many methods, including the latest technology. So this is my message. Live your engineering means it's time to drink. What do I mean by live your engineering? It means engineering is in our everyday life. So if you're putting water in your glass, you can check that there is atmospheric pressure, simply. Or you can check the centrifugal force. You can drink. You can check many things. I use forks to keep my jacket straight. But you can also check sum of forces equals 0, sum of moments equals 0. Using simple forks, you can also, one more. Let me see. This one, I need your prayers for. I'm sorry, I may make a mess. What do you think? Yes. So that's atmospheric pressure. I can keep going and going. It's really in your everyday life. So enjoy it. I have one last slide. It's about the fundamental equation of geotechnical engineering. So this is my only equation before I give the floor to the wonderful presentations, technical presentations. So to understand soil better, you have to dig deep. To understand love better, you have to dig deep. So soil equal love. Enjoy this conference. Thank you very much.
Ladies and gentlemen, just like really tiny break, just for some adjustments for the connection. We would like to invite to the stage Professor Louis, who has just left the room, and I'm not sure why he did it. Okay. So, yeah, the part of giving the souvenirs has been scheduled a little bit earlier just because our rector, Professor Zasada, he has just left. And now we would like to invite Professor Louis, who's the Vice President of ISSMGE, the International Society of Soil Mechanics and Geotechnical Engineering for Europe. We just needed really like 2 minutes to disconnect the main laptop and connect it to a Mac, which is always a confusion, as you know, because of the different plugs and stuff. So please bear with us for a moment.
So, good morning, ladies and gentlemen. Sorry for these technical things, but I'm using Macintosh, so and compatibility for videos is not that straight away. First of all, I would like to thank the organizing committee for this kind invitation. It's really great pleasure to come back to Warsaw, to come back to Poland. I would like to thank also the Polish Geotechnical Society for the invitation also, and also for all the collaboration that we are having at the European level. The Polish Geotechnical Society is a very active society in our activities that we are running under the umbrella of ISSMGE. So it's a really great pleasure to meet with them again here today. So my talk will be purely scientific talk. So I entitled the talk, even the place of the screen is not that easy, so I will be not watching and looking to you all time. I have to look also to the screen. So I entitled this talk, Biocementation, Transforming Scientific Discovery into Market Solutions. I think it's a philosophy that we should more and more develop in our way of running research activities and giving some sense also to our activities. This work was mainly possible, among others, but mainly through an advanced DRC program. Great, thank you very much. That we received from European Research Council. Now we got 3 of them. They are the most prestigious awards, as you know, in Europe. So this helped us a lot to develop what we are doing. So what I will be talking about, I was mentioning the word biocementation. So what is it? What we have behind that? Actually, you all are familiar with soil, because this is the reason why we are together here. And many of you, and I heard it yesterday already also in Poland, you have a lot of those calcium carbonate materials. So let's imagine this, we have calcium carbonate bonds, and what we will, that mainly we are getting through precipitation of crystallized calcium carbonate. So basically, if we succeed in putting those bonds inside the soil, so we will create from any loose material, so it could be sand, but could be also silt, or any loose material, a rock. This is basically what is happening in nature. This is how we are having the mountains and the rocky materials. But what we do here, we engineer them in a couple of hours. And this is what I will talk about, is how to get the biocemented materials with those calcium carbonate bonds. So basically, we are constructing from any sand, for instance, or any granular material, a rock that could have a significant strength of any cemented material. 12 megapascal is something that we can reach quickly. It's a fast process. It's bio-based, as I will mention it, long-lasting, as much as cement, Portland cement, for instance, and we use mainstream equipment. We will not disturb the construction sector, so we will use what exists already. So why our field is needing biocementation? Actually, as you know, we need more and more to strengthen our soils, our foundations. Good materials and good soils, we have less and less. So we need to strengthen, and it's known. But currently, what are we doing? In our conventional soil improvement, we use mainly cement or chemical growth. They create water pollution, grouting waste, and grouting product. So there is a major issue with our current practice, and is well known. One of the main contributors to CO2 emissions worldwide as a sector. So what we are proposing is to have a different approach using a natural process that is entirely environmentally friendly and highly efficient. So this is what we will call MICP, for microbial-induced calcite precipitation. And this we can apply to plenty of geotechnical problems, from restoration of foundations, tunneling, seismic retrofitting, and erosion, and so on. So this is what it's about. It's actually a fast-growing field, and I would even say, if you look to the 2 topics that are the hottest in geotechnical engineering publications in the last 5 years, this is one of the 2 of them. Basically, what you see here is the number of journal papers published in this topic over the recent 10 years, mainly. I published in 2013 this book on bio and chemical processes. So at that time, we were at the starting. We were considered as exotic topic by the geotechnical community. And as you can see, since then, the things are really taking over, and the technology is imposing itself. Now, as we are in the European region, I thought it's of interest to see how European area is contributing, even if we are an international conference. And basically, actually, the main contributions are coming from China, and the half later on from United States. And unfortunately, the European contribution to this field is somehow late. I think there is something, at least I'm talking as the Vice President for Europe of ISSMGE, there is something to do, but it's really important also to highlight what others are doing worldwide. We have a large number of Indian community, or Indian colleagues attending the conference here, and unfortunately, as you can see, this is a topic maybe that worth also to consider in India. There is another highlight that I want to mention, is that 90% of those work are experimental lab analysis. So this is something that somehow should be also be improved somehow. So what we try to do, so this is a topic I started to work on it almost 15 years ago, and we try to approach it from fundamental knowledge at the smallest possible scales, I would say. We work on lab scale, and very important, we move it to large scale. But we tried also to move this to advanced engineering and later on to market solutions to implement the technology in the activities. So basically, this was the content of our BioGeos effort that we are developing. So here is a table of content of my talk. I will start by discussing what are the physical and chemical processes, what are the fundamentals. Then I will explain how the injection and transport analyses are done to catch the process and to design it. I will touch then the mechanical behavior, because it's the next stage in the process when you solidify the material, and few words about industrialization of the technology. So what is the chemical process? So basically, we take urea that we mix with water, and we take a bacteria to have the process happening faster. So actually, we can catalyze the things almost 10^14 times faster than in real nature. In our case, we have our own bacteria, but there are others on the market that you can use. And from this, you get ammonium and carbonate. If you add to your carbonate some calcium, you get your calcium carbonate. And basically, what you see here on the video is calcium carbonate precipitating inside the water. Basically, this is what we are producing. There is an issue of having ammonium put in the soil, because this creates also pollution. So in our case, and we are the only ones doing this, and we are patenting it actually, we extract ammonium before putting it in the ground. So Medusoil is the name of our company. So we extract this ammonium, and we reach the same result in the ground without ammonium. So the idea is that precipitated calcium carbonate now is to put it in a porous material, in your soil. So basically, we try to have this calcium carbonate precipitating inside our porous material. And this is the goal, and this is the challenge, basically. So here you see the result of a sample. This is almost like a triaxial sample size. So what you see here in blue are the soil grains. In red are our CaCO3 minerals. And you see that we get exactly like we expected in our video. So we have homogenized distribution of our calcium carbonate inside the ground. And if you go to another scale, here 100 micrometer, you can see our sand grains, and you see the precipitation of calcium carbonate minerals. So now if we compare this to our conventional technologies and approaches, mainly using ordinary Portland cement, so if you look in terms of size, imagine this is a fracture, or this is porosity of your material or your soil. So actually, cement Portland, the smallest size that you can get or you can reach is 40 micrometers. So you cannot inject below than that. And then there are some, what we call micro cements that are meant for silty materials, for instance, where you can inject smaller things. In our case, we are going even smaller, because the limit that we are having for our solution is the size of the bacteria. The bacteria is having a size between 0.5 to 1 micrometer. So it means that we can inject something that is very fine, that is already covering part of the clays. So we can inject, of course, gravel, sand, silty materials, but also part of the clays. So then the point is that you inject this, but to fill the whole volume, because the idea is to try to fill as much as possible. So what you see here in this curve is after the post-treatment. So after the precipitation of the calcite. And what we get after precipitation, starting from 1 micrometer, we get something like it's almost 80 micrometer of precipitated material. So it means that we get something that is larger than the cement or the bentonite slurries in terms of size. So we can cover a large amount of volume. So then when we go a little bit, we upscale a little bit to see how this is happening at different stages. So now we are at 10 micrometer size. So what you see here are those precipitate, and as you can see, they are not occupying the entire volume. And basically, they are not changing significantly the hydraulic conductivity. Actually, we change the permeability by 1 order of magnitude, just that. So it means we keep porous materials porous, which is one of the issues with cement, for instance, is that you impermeabilize the material and create issues with groundwater flow, for instance. So this is not the case with biocementation. So again, let me compare on a granulometric curve with respect to many technologies that I'm sure you are all of you familiar with, from chemical grout to compaction grout to jet grouting, for instance. So what biocementation could cover is this type of size of grain. So almost we are covering the entire range of materials that we are working with. So that's it about the big picture of the technology. So now we have to look how we can design really an injection process, how we can ensure the results that we are looking for. So as I mentioned before, just to remind you, especially for those who are not familiar with the things, so I mentioned that there are 2 technologies or 2 ways to handle the things for the same technology. The first one is what we call conventional or traditional conventional MICP, is the fact that the reaction with ammonium is happening in the soil. I would say this is the largest practice, and the one that we do in our case where we extract it from the soil. So in this, in terms of designing the things, we generate 2 ways from mathematical perspective. Because basically, if you extract the ammonium before injecting it in the ground, actually what you have to consider in your reactive transport is mainly the calcite precipitation. You don't need more things because everything is made in bioreactor before injection, so you do not simulate it in your analysis. However, in traditional MICP, we simulate bacteria attachment on the grains and their decay. We simulate all the other reaction, including the calcite precipitation. So how do we do this? We use continuum mechanics. We could use mechanics of porous materials. So this is your porous material here. So there are 2 ways to design the things. Either you consider them by phases, so you can have water, calcite, and minerals, but you can consider them by species, which is more convenient for transportation and reaction cases, like you have minerals, adsorbed bacteria, adsorbed urea, ammonium, calcite, and all of them. And this is what we do. We approach the things by species, and we will describe the equations for species. So, and then what are the processes, physical processes that we deal with? So those are, first, we have fluid flow, because we inject the solution in the ground. The solution has its own fluid there, so we are dealing with hydraulic. Then this will affect the mechanics, because we change a little bit porosity. We have chemical reaction happening, and we have bacteria. So basically, we are having those physical processes that are highly coupled. Actually, when you change the chemical composition, you have a reaction rate for the bacteria, and when you change permeability, you change porosity, and then you can induce deformation and all those things. So the process is highly coupled process, and we need a given number of equations to solve it. And basically what we did with is fluid flow, equilibrium, and component of transport, and we write all those equations. I will show you briefly how we do them. So again, now we simplify the process as I was showing you before. We write our species, so we write conservation equation for each of those species, and depending whether we are dealing with traditional MICP or ex situ MICP, we will not have the same number of equations, but we have all time the needed number of unknowns, so the system is equilibrated. So basically, the fundamental equation is the mass balance. that we have to ensure for all the species, so they are very familiar for those among you who is familiar with the mechanics of porous materials. So we have the accumulated rate in the species, we have the convective flux, then we have dispersion and diffusion. So, and we add to that for partially saturated conditions, the Rector equation, because we make the hypothesis that during the process of diffusion of the fluid, we are not changing the porosity. So we can consider Rector equation valid. So we need to add constitutive equations to the system. So if we are in ex situ hydrolysis, so we have the precipitation rate, so we have to know how much we are precipitating from a given number of calcium carbonate, calcite precipitation, how much porosity is changing with this precipitation rate. When you change porosity, you introduce your new value of porosity in your permeability equation, and you have dispersion and diffusion that you have to consider in the medium. If you extend to traditional MICP, we have to have the hydrolysis equation that has to be considered in the system. So at the end, we come to this system of equations, more or less 7 or 8 equations, depending whether we consider the effective stress and mechanics or not, with the same number of unknowns. And I think which is more interesting for you just to see is what type of coupling that we are dealing with. So basically, those who are familiar with Biot theory for consolidation, for instance, this is mechanics, this is flow, so this is a hydromechanic coupling, so which when you change pore water pressure, you induce change in porosity. This is variation of displacement. Then you have all bacteria and chemistry interactions. So when you have precipitation rates, those change in precipitation rate will induce change in the chemical composition for the calcite precipitation. And then you couple everything. So in your conservation of mass, you add the effect of the bacteria and all the chemical terms to have the whole system coupled. And this allows us now to have a design tool that allows us to know which pressure we should impose, which area we can cover, and which concentration of calcite we can get. And this is the most important parameter for us. So to validate such numerical or such theoretical approach, we constructed a unique of its kind worldwide facility to test our conditions of behavior of the material in almost similar conditions like in reality, in situ. So what we are having, we have this 2 compartments. Each time we try to have one where the material is untreated, so we do not inject anything as a reference case. And then a second compartment that is treated. We have 16 injection wells. We have drains that are incorporated to control the partial saturation. And basically, we have 2 times 75 cubic meter of soil. So let me show you some results. So this is first, an untreated part, so we can analyze the things like with the dynamic penetrometer. So this is at different depths, and basically we see that we are having a small values of resistance in the material. And now I show you the case of a treated material where we inject the things, and basically you see that we are going towards a yellow part of the thing, so it means that we are increasing the strength of the material. This is a global view, but let us look to it in more details. And basically, the results that I will show you now are based on almost 29 untreated tests and almost more than 40 treated tests. So we have a large statistic database for the results. So what you see here are 2 values of the dynamic penetrometer results here at a short distance, for one of them 20 centimeter and 75 the other. So they are the values before treatment, and now you get the tip resistance in the ground after treatment. As you can see, we are moving almost from 0.5, if not 0 megapascal, to 3 megapascal of improvement in the ground. So then we look at 2 different ways to ensure first the homogeneity, for instance, by using slip pipes systems. And you can see here we can go until almost 4 megapascal. And we can go even further, for instance, if we use tube manchette system after different recycling, I think in this case it was 3 times injection, three injection in the ground, we can reach almost 20 megapascal of tip resistance. So this is just small videos to show you how is the shape. So of course here we extracted all the sand that was not affected significantly, and what remains is the biocemented things. And our design tool was actually validated somehow, if we can talk about validated, through those results where we did, as I said, a large number of those tests. Now the question is, how are we able to simulate and to predict the mechanical behavior of the material after cementation? So before going that, so I show you ways of validation of the model. So here I'm showing you a case of injection in saturated soil in ex situ hydrolysis process, and basically without going in details, what we can show is that the model, our numerical fine-tunement analysis, allows to get the calcite precipitation diffusion, allows to control what are the pressures to inject and different conditions. Second and last case, for instance, we look to a single wall. So in this case, we are in partially saturated condition with the traditional MICP. And again, here we look at different configuration to optimize the process. And we do it now numerically because we don't need to have this parametric analysis done experimentally, because we have confidence in the model and we see how much we can get of this calcite. Important aspect here, it means that we have to control and we can manage the calcite. So we don't need to work all time the same calcite values, and then we come back to this. So I discussed the injection process, I discussed the transport, I discussed the reaction. So last remaining item is the mechanical behavior. How much strength we are getting after our injection. So here are unconfined compressive stress strength test that we did almost a long time ago. So, and basically what you see is that we have the increase of the compressive strength with the increase of amount of calcite precipitation that you put in the ground. The same thing with the stiffness. So this is Young modulus with the calcite precipitation. Again, we see that. So from this, we came with the fact that we can actually create categories of improvement depending on the needs. So for instance, if you are dealing with liquefaction and erosion protection problems, small amount of calcite is sufficient to create the needed cohesion in the material for that. If you have to increase the bearing capacity, so you can increase a little bit the domain, and then you can go for something strength with higher strength, as I was mentioning, almost 12 megapascal. So briefly, those things are conventional geotechnical things. So we did several odometric tests on materials so different type of sands at different amount of calcite precipitation to understand what's happening. And basically what we see, we have stiffer material, so the slope is stiffer, and we have a kind of a pre-consolidation stress that is decreasing, so like we are plastifying the material. We did also triaxial tests on the same type of materials. So you see here the shear plan for different confining stresses. And then after treatment, in this case, it's 8 megapascal. And you see that we move from something like 200 kilopascal to almost more than 2,000 kilopascal of strength for those materials. And when you look to the friction angle at the peak, it's not that much changing, but we are creating significant cohesion, almost 400 kilopascal that is created, for instance, in this case. The volumetric aspect is a little bit also affected in terms of the latency, because we are creating like over-consolidated material, so necessarily the dilatant behavior is affected. Last experimental things, this is the only result that is not coming from our group, is a cyclic direct shear test, where the authors, Lee and all, they tested first a material that is not treated, and then they tested the same cyclic behavior of the material after small treatment, 0.5 of calcite content, and you see the number of cycles needed to get to liquefaction is huge. So With this, we are decreasing significantly the liquefaction potential with just 0.5% of calcite precipitation. So we try to understand what are the physical processes behind this change of the rheology of the behavior to be able to incorporate them in a constitutive manner. So for that, we move it to really fundamental science and going to very small scale, 0.1 millimeter, and we use it what we call microchip technology with microfluidics. So basically what we did, we took two of those elements that you see here. This is a microchip that we constructed. This represents 1 meter length of a porous material. So here I'm showing you two of them, 1 meter length, that are very small when you see them. It's a centimeter scale, as I was showing you. And we can follow what is happening inside those ships in real time. We follow all the process of crystallization and what is all the things happening behind it. So I will show you results of two cases that they are having the same porosity, but the different distributions of grains. So the system is based on the fact that we inject first with syringe pump our bacteria solution from one side, then we inject from the other side our cementation solution that mainly is urea, and we use cameras to follow what is happening in the PDMS ship. So basically, this is type of result that we can get. I'm showing the results almost in the middle of our 1 meter long ship. So if we are in this first case of unifiedly distributed pores, we see first that we are having two kinds of contact. Some of them are making contact between the two grains and others just covering the grains. We see it better in a heterogeneous case, and here you have the time running, so all the process is happening in 24 hours maximum. And here we see it better. We have what we defined as two groups, the effective crystal effect that really creates glue between the grains, like this one. Okay, if I get I lost it. And those, like this one, where they cover the grains, but they are not creating the glues. So they change the porosity, but not clear. So there are those two rheological processes that now we would like to introduce in a constitutive way to be able to represent the evolution of the behavior of the material with biocementation. So here it's another scale that I'm taking. So we took those pictures just to show you that from one side we see those elements of calcite that are not creating the glue but densifying the material. And from the other side, we have this cementation that is happening by putting direct contact between the grains, creating this biocement. So to do this in terms of constitutive law, so you can take any constitutive model that you are familiar with and you induce in it those rheological processes. In our case, we took a model that I'm familiar with. It's a Hughes model that we extended to bacteria and chemistry for biocementation source. So it's a nonlinear elasticity model. It's a elastoplastic model. It has a yield limit that's very similar to CAM clay. For those who are familiar with CAM clay, there are just a few differences. So instead, the capital M, it's a sinus here. And it has this shape, and because it has a fourth mechanism that cut in the isotropic limit. So this is the elastic domain. It's a model like any other model. It's of interest for us, this model, because it has a cyclic mechanism in the behavior. So what does it mean? So now I write the same equation that I was showing before. We write it in a different mathematical form that allow us to normalize the things and to have it in terms of circles. So in one of the mechanisms, so this would be our elastic domain, and then when you load your material, you have an hysteretic domain, and when you unload it, you have it with the plasticity and unloading. So this is what we call kinematic hardening. So this is the motivation for us in using a model with kinematic hardening. So in this model, we will introduce now the two processes that I mentioned before. First, densification, so we have to do it in an elastic part and in the plastic part. So the elastic part, we do it, oops, too fast. Elastic part, we do it by changing the bulk modulus and the shear modulus, because by changing by this coating of crystal around the grains, we are changing the bulk modulus and shear modulus, and we do it in this mathematical way, where we relate this to the amount of mass that is precipitating in the soil. From the bioplasticity part, what we do, this precipitation around the grains is reducing the volume. So basically, we represent a reduction of the volume, and if you reduce the volume, this is normally consolidated line, so you are changing your pre-consolidation stress. The other aspect is bending, as I mentioned. So the bending, we do it also for elasticity and plasticity. Again, we introduce a new coefficient for the elastic parameters. What's more important for the plastic part is that this bending coefficient represents the fact that at very high shear stress, we will have destruction of those bends. So we will move from a large normally consolidated line to come back to the untreated normally consolidated line, like we do it for structural materials, for instance. Last rheological aspect is about the elastic domain. So in the elastic domain, we have the G gamma curves. Those who are familiar with soil dynamic analysis. So basically, our G gamma curve will change in the fact that we are changing the shear modulus values by introducing bonding and density. So, and at the end, when we reach the values of distortion, let's say of 0.5%, then we recover the initial value. So the yield limit that we get at the end is this type. So we start for untreated case. This is, I said, it's almost a modified template that you cut here with the case where you are able to get this increase of the peak strength of the material. There is also the latency part that I will not discuss. Just quickly, some model performance. So here are experimental results from the literature that we are simulating in different cases, but in all cases where you see what is the treated and untreated case. So the model is able to reproduce and to move from, let's say, type of normally consolidated behavior to an over-consolidated behavior with a critical state that is not that much affected at the end, and also in terms of the latency, observed things. More interesting is for the cyclic loading, because I was mentioning the liquefaction process. So here the model also is able to represent, so this result, it's almost in one cycle, going and coming back, so the authors were able to get liquefaction of the material. So here you see the original model representing that liquefaction. However, now what we are having is that how this liquefaction potential is increased by increasing the calcite amount in the soil, and you can see the model is able to represent even the number of cycles needed to reach liquefaction. Last curve related to model performance is the same results as before, but here are represented in terms of number of cycles to liquefaction. This is the cycle-stress ratio. And again, you see comparison between the experimental results and the numerical model are pretty well. Last aspect, so based on all those things, so we move it to industrialization process. So what first achieved is that we developed 3 patents to protect the technology from first system injection, then of this extraction of ammonium before injection, also coupling this with geosynthetic. So we did them, and we built a company to commercialize those things. And the principle of industrialization is the fact that we have zero waste manufacturer. So those manufacturers could be on site, but we have also mobile manufacturing or production units. So currently, for instance, we are having a project since 2 weeks in Romania, where we shifted our mobile unit. So basically, we have everything growing in a bioreactor. Then we come on site, we inject from our one part our solution. From other part, we provide calcium that is available anywhere, and we generate calcium carbonate in the ground. So let me show you some examples, quickly 5 examples. First one, stabilization of micro-terrain excavation. So as I was mentioning, each time we have calcium coming from one side, we have our solution from the other, and we inject them together, and the precipitation happening in the ground. So we use a very simple technologies, for instance, because the pump, we don't need a lot of pressure, is 1 bar of pressure that we inject in the ground, as you can see, and basically with the requested precipitation of the calcite in the ground, we were able to stabilize an area that initially the microtunnel would not be able to move without reinforcement. So this is a way to show how it's performing well. This is another case. It's a slope stabilization. Again, each time you see our solutions. From one side, you have our BS solution, other one, the calcium. And what I was showing you here is the tip resistance. So here we have a slip surface that is at 1 meter depth. So the idea was to reinforce mainly the slip surface, because it's there where we are having the failure. And basically, this is what you observe here, is that before the tip resistance was rather quick, and this is around 1 meter. So here what you see is the technician reaching exactly the place where we are targeting the reinforcement. Third example is gravel tip slope reinforcement. When you have those large areas that are facing erosion, to stabilize them, basically here is what we turn erosion path in biocementing path by simply splitting the solution on the surface and getting the needed stabilization. Another example, sandstone cliff stabilization. So basically, you see we have this cliff here that was start to be dangerous for road circulation, and we were asked to stabilize. Here is just to make the boreholes. So we'll shift a little bit the video. And basically what I can show you is the result after injecting this time horizontally the solution over 2 meter depth. You see, actually, this is the seismic wave velocity that you see here. So initially we were like with having a sand, and we are getting a rock after 2 days. This is the initial one, and we are getting a rock after 2 days. 2,000 meters per second is more or less a rock already. Last example, terrain platform erosion mitigation. In many of those examples, actually, that I'm showing you, the technology have also a great advantage, is that we use materials and way to proceed that actually do not request, for instance, to stop train circulation to make the reinforcement. So you can do it really in a very light way, because we use really simple things. So and here we can see is just the values that we are moving from something like 15 kilopascal of initial cohesion before reinforcement to more than 200 kilopascal. So my last slide is about environmental impact in comparison with the conventional technologies. This is done by an independent company, Cantis, who can quantify CO2 emissions of different technologies. And we did it on the 5 projects, for instance, that I was showing you there. And at least there is more than a half of CO2 emission with respect to conventional cement grouting technologies. So my conclusion will be very brief, because I think I said the most important things, and you were able to follow me from trying to start from fundamental science to understand really what is happening at the smallest scale, what are the physical and chemical processes. We try to translate that in a mathematical ways to have design tools. We try to understand the mechanical behavior of the material after biocementation to be able also to predict it for design purpose. And then we move the technology to the industry and to the market by patenting things and by producing really engineering solution to the benefit of the society. Here, large group of people working with me in my research group at EPFL who contributed to the activities. And here are my collaborators of my company, Midwisoil, who are making the industrialization part of the things. Thank you very much for your attention.
stay at the stage, and we have some souvenirs for you.
Now is coffee break. Welcome.
Zostaje, czyli 4.
Jest jakaś tego, tak? Teraz jest pół godziny przerwy. Natomiast jest tam jakieś kawa, herbata, tak?
Tak, ciastka jest, wszystko jest.
Dobra, Krishna. Kto teraz będzie? Andrea. Jaki to podskładam na rozmowę? Nie ma zasady.
Zasada jest po prostu
I Krishna też zdejmujemy. A nie, Krishna będzie, bo teraz on będzie wygłaszał, tak?
Nie, w sensie, że jest pod spodem zasada jest, pod Kriśnią, o, tu jest zasada.
Też zasady
Teraz
nie ma.
mamy w zasadzie,
Zasady
możemy tak mieć Kriszna, Dominiani, Zabielska. Denes, tak. Denes, tak. No nie, to trzeba jej 6, tak, to raz, dwa, trzy,
To
cztery.
ja tutaj
To za-
z nimi, tak?
To na zmianę.
Ja sobie
Tak, to ja to wezmę. Trzeba skończyć wymienię.
Ale gdyby Pani chciała, to tutaj na mównicy jest mysz i wtedy
Nie
Pani
będę
sobie...
pokazywać, jeśli tam coś, to po prostu 1 lub 2 razy, także
Ale
spokojnie.
to i tak tu Pani sobie robi, tu Pani patrzy, nie? Żeby nie było tak jak podczas tej prezentacji, że ten Pan stał...
Nie, no ale normalnie to tak się powinno robić jak profesor.
Nie, to jest
Tak.
największy skandal. Pani wie.
No nie, no.
I to, ale
Around the time, we should probably move on to the next session, the main session, with the keynote lectures. So, especially to the people outside, if you haven't finished your coffee yet, please bring your cups. It's absolutely fine to have it here in a hall. And next 5 minutes, I think we all should be ready.
Good morning, everyone. It's 6 minutes past 11. Let's start the session. If for the folks who are still outside enjoying the coffee, appreciate it if you could come back in. So, this one
Because
works?
this one is not sending to the TV. It's not streaming.
Okay, folks who are enjoying the coffee break, we'll appreciate if you could come back in. We're 6 minutes behind.
Oh my God. 6 minutes.
Let's give it another 30 seconds. And wait for everybody to settle in their seats. Okay. Thanks everyone for being here. It's my pleasure my name is Arvin Farid, by the way, from Boise State University, United States. It's a pleasure to be here in Warsaw among close friends and making new friends here. It's my pleasure to introduce Professor Krishna Reddy from University of Illinois, Chicago. He is a distinguished researcher and the director of Geotechnical and Geoenvironmental Engineering Laboratory and Sustainable Engineering Research Laboratory at University of Illinois, Chicago. And I know Professor Reddy since 2008, I think. I had just started my career. I thought I was young back then. He was young, but he was a star back then. And he was the chair of the Geoenvironmental Engineering Committee of American Society of Civil Engineers. And it's now 16 years later. I'm getting old, and he looks younger. So every year we receive emails with his accomplishments of the year. It looks bigger than everybody else's CV, including myself. So you think it's just his CV is just that one single year. So he's done a lot of work in a lot of different fields, including a lot of geoenvironmental engineering and environmental geotechnology research. It's my pleasure to invite Professor Reddy to the podium. With no further ado, the floor is yours.
Thank you so much. So good morning. Good morning. It's working. Okay. Yeah. Okay. So good morning, everyone. Thanks for attending this conference. As I mentioned during my opening session, this is a very unique conference where we learn not only the technical stuff, but we make professional connections. So I'm going to talk about a topic that you may or may not be familiar. It's called biochar. I am from University of Illinois, Chicago. I work on different areas, even though I'm talking about biochar. My areas of research are environmental remediation of soil, sediments, groundwater, and stormwater. I also work on waste management and landfill engineering. I work on life cycle assessment, sustainability and resiliency, and I also work on geotechnical engineering. So I work on a lot of different topics, but I wanted to choose a topic that is more relevant and for research that's going on these days. So you can find more information about my research on these websites. First of all, let me ask audience, how many of you know what is biochar? Can you raise your hand? So just to see very few hands up. So hopefully by the time I finish my presentation, you will understand what biochar is. So what I'm going to do now in this presentation is I'm going to explain what is biochar. And then I'm going to say biochar as is not always enough. So you need to engineer it or modify it. I'm going to explain why we need to do that one. What are the ways that we can modify the biochar to meet the requirements? And then I'm going to show you there are many applications in many engineering fields, even in geotechnical engineering, and I'm going to focus more on geoenvironmental applications. And then, there are a lot of research challenges and a lot of opportunities. There is a lot of scope to do research on this topic. So I will point out those things at the end, and I will close with some closing comments. What is biochar? So there is no universally accepted definition of biochar. There are some agencies like International Biochar Initiative, it has a definition. US Biochar Initiative has its definition. European Biochar Certificate has its definition. And International Union of Pure and Applied Chemistry has a definition. US Department of Agriculture has a definition. Biochar International, this is one organization that has a definition. And then Institute of Food and Agriculture, University of Florida has its own definition. So there are definitions, many different definitions given by different agencies. But you don't have to get confused with all those definitions. You should know this common definition. What is common definition of biochar is? Biochar is nothing but a carbonaceous material, basically carbon material, that is produced from thermal decomposition of organic matter in the absence of limited or no oxygen presence. Okay, in the absence of or limited supply of oxygen. So basically, it's created from thermal process of organic matter in the absence of oxygen. So that's a kind of a basic definition. If you can remember, that's fine. And biochar has been receiving tremendous interest of researchers, tremendous amount of research. So this graph is really mind-blowing. For example, look at it. So how many publications have been published? You can see how the evolution of publications. Those bar charts are the number of publications published in a year. It's not cumulative. Cumulative is that line, you see it. Look at how many publications last year. Close to 7,000. Before that, 6,000. Before that, 5,000. So if you look at 2013, there are not many publications. But if you add up all the publications as of now, you have about 37,000 publications. So this is really, a lot of people are doing research on this one. So you really need to know what is this that is attracting the attention of a lot of researchers, right? So you don't want to be left behind. So hopefully my presentation can help you understand what biochar is, and maybe you can pursue some research on this one. As I said, biochar is basically produced from biomass. So biomass could be anything, as you see here. And then basically you are feeding into this thermal heating unit called pyrolysis. And in this one, you heat it up to some certain temperature without letting any oxygen in. And when you do that one, you're going to get this biofuel, syngas and pyrolysis. So this has been going on. So basically, this is the way you produce the alternative energy, right? So a lot of people who work in the energy area, they work on this one because they're converting, organic waste into energy. But as a byproduct, you get this material called biochar. Biochar is similar to charcoal. So as I said, pyrolysis is basically you are heating up that organic matter at temperature ranging from 300 to 800 degrees centigrade. But depending upon how you are doing pyrolysis, it can be classified into two types of pyrolysis. Slow pyrolysis is where you slowly increase the temperature to the highest desired temperature. It could take several hours. That's called slow pyrolysis. The fast pyrolysis is you don't wait it, just heat up the temperature to the desired value and heat it up the biomass. So that is called fast pyrolysis. So that takes only a few minutes. This is hours. And these are the pyrolysis units. So you can get lab scale, mobile scale, very large unit. So which is nice. If you want to create a biochar at your project site, you can do it. So you can, you don't have to have a huge plant like this one. So you can have a mobile plant, and then you can do the project wherever you want. But the pyrolysis conditions, if you look at the literature, it varies a lot. The temperature could vary from 100 to 1,000, residence time 1 to 10 hours, heating rate 1 to 20 degrees centigrade per minute. So there are many studies. You look at it, I kind of try to consolidate all that information there. And there are other biochar production methods other than pyrolysis. One is called gasification, other one called hydrothermal carbonation, other one called torrefaction. So you need to remember there could be other than pyrolysis process to produce the biochar. So biochar is produced from biomass. Biomass is basically organic waste. Look at all these types of organic mass. So banana peels, like all these things. You can have a chicken litter or pig litter. Sludges. You can see all kinds of stuff that rice husk, all the organic waste that you have, that can be converted into biochar. So biochar is made from organic waste. In terms of waste management, organic waste is very difficult to get rid of it. So here you can use the organic waste to produce the biofuels, bioenergy, and also the biochar. So just I'm giving you some idea about the different types of biochar. All this information is in my paper that's going to be published in this conference proceedings. So there are different types of wood-based organic waste. Then you have different types of plant-based organic waste. Right here, you can see it. And you could be animal-based organic waste. You can see this one. And you could have other waste like a sewage sludge, municipal solid waste, all these organic waste. Any type of organic waste that you have that can be used as a biomass or feedstock for creating the biochar. In terms of the quantities of the organic waste we generate, it's a lot of it. So, agriculture waste, for example, so this, we create 1,000 million tons per year. So that keeps on accumulating if you don't do anything. And municipal solid waste, is 2,000 million tons per year, but out of that municipal solid waste, more than 40% is organic mass. So you have organic fraction. So all this can be converted into biofuel and bioenergy. So biochar, when it is produced, it will look differently depending upon how you subject the pyrolysis process. So this is the kind of pictures of different types of biochar when you produce it. Biochar has a very unique properties. Right? What are these unique properties? For example, chemical properties. It has a high surface functional groups. They play a major role when you are doing using this material for treatment purposes. And you have a high cation exchange capacity, favorable mineral content, high carbon content, conducive to oxidation, and it has an alkaline pH. And it has unique physical properties, high heat capacity, high water holding capacity, highly porous structure, which is very important. And it has stable structure. It does not degrade. Or the biochar is going to last for a long time. And then it has high surface area. These are very unique physical and chemical properties that you can exploit for various applications. Now, there are many different applications. You can use as a soil amendment for different purposes I listed there. And you can use for greenhouse gas emissions control. So there are many applications there I mentioned. And for contamination removal, water, air, soil, wastewater, you can use this material for that. And you can use as a construction material also in this one. And you can use, not only in the civil engineering field, people are using in electrical and chemical applications. So many applications for this material that is made from biomass, it's organic waste. And if you look at a big picture of the implications, the biochar use can contribute significantly to sustainable development goals. So I listed a few of them, 6, 7, 13, 12, 11, 9 as examples. So you can see, this has huge implications even in a sustainable development point of view. Okay, so that's about biochar very briefly. So I hope you understood what biochar is. Now, biochar is not always has the properties that you need it for your specific application. Let's say, you are working on some project and you need a material, but the biochar does not have the properties that you want. Why? Because, this has a limited contamination range. Let's say if I'm dealing with wastewater or industrial water or contaminated soil, I have contaminants, maybe this material is not good as it is, as a biochar. Limited absorption capacities, limited anionic capacity, high ash content, impurities, high volatile content, low density, small particle size, low active sites, harder to separate from aqueous media, high dependence on properties of biochar on the preparation conditions and feedstock. So those are the problems. But you cannot be discouraged by those problems. If those problems are not favorable to you, you can modify them. That's called engineered biochar. So you can modify the biochar in different ways. So here you have a biomass, and you do the pyrolysis process, as I said, these different processes, and then you produce the biochar. And then this biochar does not have properties that you want. So you need modifications. So this is the post-treatment modifications. There are different types of modifications, physical, chemical, biological, magnetic, and you can create composites. And then when you do that one, you get an engineered biochar or modified biochar, okay? And this can be done in a different ways. You can treat the biomass and then subject it to, you have a modified biomass, and then subject it to pyrolysis, then you can also get a modified biochar. So which route you take it, the treatment is a post-treatment or pre-treatment. You can do either way. And then you have these different options to do that. Now, so in the physical treatment, if I want to do the physical treatment, there are different ways to do the treatment. If I want to do the chemical treatment, there are different ways to do it. If I want to do the biological treatment, different ways to do it. Magnetic modifications, you can do it. And you can combine this biochar with other materials, and then you can create a biochar composite, right? And in my paper, I provide all these details, so don't worry about not losing this information. Now, the treatment that you have to do is it has to give the improvement that you are looking for, right? Biochar, as it is doesn't have properties, but you are looking for some improved properties. And you need to tailor the treatment to get the improvement that you want. For example, among the physical, so you can have just a ball milling. Basically, you can reduce the size. People create the nano biochar, and it has high surface area, and it has unique properties to serve certain functions that is based on the nano size. So like that, if you look at the chemical, for example, if I use this kind of a modification, I can get a high surface area. And then, I can use the biological process, and you can, activate it with the microbes, and you can get, bioactive biochar. And you can use the composites. You can, add biochar with any of these materials, including clays. For example, we are working on with a composite biochar, chitosan composite, that can really give very unique characteristics to the biochar that can help us in our applications. Okay? So now, let me summarize what I said. Biomass type. What are the different types of biomass? Based on the literature that we found, there are more than 70 types of biochar, the biomass types people have used to create the biochar. Now, what are the different ways to produce the biochar? There are 4 different ways to produce a biochar, right? And then in the production method, you have variables. What is the highest heating temperature? What is the residence time? What is the heating rate? The combinations of those can result 1,890 combinations. And then modifications. So after you make the biochar, if it is not good enough, then you have to do the pre-treatment. You can do the physical, chemical, biological, magnetic, or post-treatment. You can do that one. That combination is 30%. So let's say permutation combinations. How many types of biochars you can have? So 70 times 4 times 1890 times 31, that leads to 16 million types of biochar. 16 million types of biochar, right? So the point that I want to mention is when you are looking at the literature, whenever you are looking at the publications on biochar, be mindful about what is the feedstock, how it is produced, what are its characteristics. You may be talking about different material, so that's why in the literature, everybody uses in the title biochar, but out of 16 million, which one you are talking about, right? So this is the important point to remember. And this biochar can be used in different types of applications. For example, contamination remediation, as a soil amendment, as a bioenergy, as a climate change, waste management, and as a construction material, geomaterials. So many different applications, so many different applications. So just, after my presentation, think about, you are doing some research, you can ask yourself, can I use biochar in my research? Okay? If you want to discuss with me later on, I will be very glad to discuss that one. And then it's unique, because if I work on contamination remediation, so look at that. When you modify the biochar, you get these unique properties, and that can take out different types of contaminants I'm showing you here. So for environmental remediation applications, the modified biochar is the best that you can think about. So we do a lot of research on biochar at UIC. For a long time, we have been doing for last maybe at least 15, 20 years. So these are the kind of projects that we worked on. We used as a filter media for stormwater treatment, biocover for enhanced landfill methane oxidation, and we used to stabilize the heavy metals in contaminated soils, and we used as an organic amendment in phytoremediation projects, and we have a project that's going on right now. We are creating a biochar chitosan or biochar chitosan and bentonite composites for barrier applications. And you can use for, just even geotechnical purposes. If you want to interested in improving the mechanical strength, you can use this one too. So one thing that I want to mention is a lot of studies just deal with lab scale studies. But you really need to go out to the field and try to see what you found in the lab is applicable or not. When you are doing the full scale applications, you need to look at what is my source of biochar is. Because a lot of people make biochar in the lab using the lab scale reactor, 100 grams, 200 grams, and they do the research on that one. But when you are doing out in the field, you need tons of material. So where you can get the tons of material, you really need to match it, right? You have to look at the material that is going to be available for field applications. And I love doing the field work. That's the pictures of me working at a landfill site with my students. So there are a lot of information on my previous projects. So just the challenges, okay? It's a very confusing. Hopefully you understood what I meant by. There are no standards for producing the biochar. Everybody is creating their own biochar in different ways. So as I said, like you're creating one of the 16 million biochars. Which biochar you're producing? There is no standards. There are no standards for applications of biochar. Okay, I want to use for wastewater treatment, but there are no standards on how to use biochar for that application. Inconsistent or contradictory research studies. You get frustrated when you review the literature on biochar. One study says this, other study says this. And it is possible because you are dealing with totally different material, right? So that's a really huge problem when you are doing the literature review. Don't let your students ignore things that you don't like it, because if somebody says it doesn't work, you can understand why it doesn't work, but that particular biochar may not be useful. So not all biochars are the same, there are variable properties. And biochar modification, if you modify a biochar for one particular application, same thing is not applicable for other applications. So the modification has to be focused on the application that you are dealing with. And you don't expect that modification to work for other applications. And the problem is with biochar, a lot of studies are lab scale studies, not many field scale studies. So you really need to focus on field scale studies and what are the issues that are learned by doing the field scale studies. And then, is the use of biochar economical? People argue that, hey, I'm using the organic mass, it's cheap. Not necessarily. So you really need to worry whether it is truly economical or not, because it depends upon the biomass sourcing, and where are you making the biochar? What is the transportation distances involved in that? What are the other logistical issues involved in that? So the cost not always cheap, okay? So you have to keep in mind. And the other question is it sustainable? People say that, using the biochar is a sustainable option. Not necessarily. You really need to, depends upon the specific purpose, method, and application. You really have to quantify the sustainability and see that it is indeed sustainable from the point of view of broader environmental impacts, economic impacts, and social impacts. So you really need to quantify, because just using biochar is a sustainable material is not true. Now that's the challenges, but the opportunities. I like the opportunities a lot. That's why the challenges, you should try to overcome those. First of all, you are converting organic mass into renewable energy source. Who doesn't like that, right? Otherwise, garbage is going to be all over. You're converting organic waste into renewable energy source. You know that any alternative source to fossil fuels is the great thing these days from a climate change point of view. And this supports the circular economy. You are converting the waste into beneficial use, and so it's a better solid waste management. And then you are doing the carbon sequestration and addressing the climate change mitigation. As I said, there are many applications, but I work in geoenvironmental engineering field, and I can see many applications in geoenvironmental engineering field for waste containment, contaminant remediation, soil quality enhancement. And you feel good about doing the research on this one because you are contributing to broader good of sustainability. And the last point I want to mention is opportunities outweigh challenges. The challenges should not be discouraging to you because the opportunities are really much greater, but you should focus on the research not for limited lab scale, but take them into applications. Just the last slide in the closing comments, just the takeaway points from all my presentation is this. The biochar production and applications provide multiple benefits, including energy production, circular economy, and sustainable development goals. Biochar offer potential solutions to many engineering challenges, particularly in geoenvironmental engineering. You can achieve desired properties of biochar by selecting appropriate modification techniques. And you can achieve sustainability benefits provided you are careful about how you use it, in which applications you use it. You need to do the assessment and make sure that it is right. And the biggest concern, is that we don't have standards for production, properties, and applications. So hopefully they are going to come up very soon. So the biochar does, it does not say anything about soil, but biochar and soil combinations are plenty. The geotechnical engineers, geoenvironmental engineers, and civil engineers in general can benefit by using the biochar in combination with the materials that people deal with. So I want to thank Professor Koda again for organizing this conference. And I want to thank my graduate student who helped me to put this presentation together. And we have an ongoing research project funded by National Science Foundation. I want to acknowledge their funding help. So thank you so much for listening to me.
Just for your information, question and answers actually only from the committee ward. We will leave the discussion in the couloirs later on after lunch or during the lunch break. Thank you.
Okay, thanks, Professor Reddy. That was an engaging presentation as always and transformative too. So after Professor Reddy's talk, I'd like to introduce Dr. Andrea Damengiani. He's an associate professor at the Politecnico di Torino, where he received his PhD as well in 2005. His research activity is devoted to ground improvement methods, containment systems for landfills and polluted sites, and chemomechanical phenomena in clay soils. He's currently the chair of the Technical Committee TC215 from ISSMGE, International Society of Soil Mechanics and Geotechnical Engineering, and he held the position of the secretary of the committee for 11 years, 2010 to 2021. With no further ado, the floor is yours.
Thank you very much for your kind introduction. I want to thank the organizing and scientific committees, in particular Eugenio Skoda and Krishna Reddy, for inviting me to deliver this lecture. Moreover, I want to express my gratitude to our president of ISSMGE, Mark Baluz, for celebrating Michele Jamiolkowski's memory. As you know, Michele Jamiolkowski was the founder of the School of Geotechnical Engineering at the Politecnico di Torino, my university. And I can say that we all miss his presence, his teachings, and above all, his guidance. So thank you very much for celebrating him on this occasion in his home country, with which he had maintained always close relations and which he loved very much. Thank you again. So the title of my presentation is Risk Assessment for Sustainable Waste Disposal to Landfills. This is the outline of the lecture. I will start by introducing the concept of sustainability, then I will discuss how sustainability criteria may be applied to the design of landfill lining systems. The presentation will continue with a description of a set of analytical and numerical solutions to contaminant transport from a landfill that have been developed to assess the risk for human health and environment. In conclusion, I will describe an application example and I will provide some final comments. I introduce now some basic ideas related to the concept of sustainability. This concept has emerged in economic studies that were conducted in the 70s of the past century. In the beginning, it was regarded as the capacity of human habits and actions to be practiced or maintained indefinitely, as suggested by its etymological derivation from the Latin word sustinere, which means hold upright, and also bear, undergo, endure. In this initial usage, the concept of sustainability was not characterized by any ethical implications and was strictly related to the concern for maintaining the availability of desirable materials and conditions over the long term. Sustainable forestry, for example, limits the annual harvest from forest to allow sufficient regeneration so that a similar harvest can be taken every year into the indefinite future. A similar idea is that of sustainable fisheries. However, when applied to human actions impacting the environment, the concept of sustainability has assumed a new and deeper meaning. In particular, the conferment of an ethical value has connoted this change. Sustainable practices have been identified through their capacity to provide for the needs of future generations as well as the present. This paradigm shift is represented by the definition of sustainable development provided by the United Nations Commission on Environment and Development, the so-called Brundtland Commission, from the name of its chairperson, the former Prime Minister of Norway, Gro Brundtland. This commission published a report in 1987 titled Our Common Future, in which sustainable development is defined as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Responsibility to future generations is the fundamental duty of environmental ethics, and it has its roots in the following reformulation of the famous Kant's categorical imperative formulated by the German-American philosopher Hans Jonas. Act so that the effects of your action are compatible with the permanence of genuine human life. This new imperative entails that we must ensure that the effects of our actions do not destroy future genuine human life. To ensure genuine human life means to protect the future humanity's autonomy, dignity, integrity, and vulnerability. But this in turn requires the preservation of nature, so that future generations can have the best possible living conditions. Let's see now how sustainability criteria may be applied to the design of landfill lining systems. The application of sustainability criteria to the design of contaminant barriers implicates balancing two conflicting needs. The first need is to maximize the protection of groundwater quality. The traditional method to meet this need is to increase the thickness and reduce the hydraulic conductivity of the low permeability mineral layers of the lining system. The consequence is accepting high economic cost, elevated consumption of natural hair materials, and substantial emission of greenhouse gases for the transportation of raw materials and the construction of the lining system. The second need is to reduce the economic and environmental impact of barrier construction. This second need requires reducing the use of engineered barriers and relying on natural attenuation processes which are affected by high uncertainty. In this case, the consequence is accepting a possible high risk for human health and environment given by the contamination of the groundwater. Now, from my point of view, a fundamental innovation that has been developed to face this problem is represented by the transition from a prescriptive-based design approach to a performance-based design approach. The performance-based design guarantees to protect the groundwater resource, avoiding recourse to oversized lining systems with relevant economic and environmental savings. The modeling of contaminant transport that takes place through mineral and geosynthetic liners allows for a rational design of the barrier system components and the quantification of the expected performance of the wall lining system. avoiding the construction of oversized barriers on the basis of the so-called precautionary principle, which is typically invoked when a theoretical analysis is not carried out. However, we must take into account that the responsibility to future generations that we mentioned before, implied in the concept of sustainability, requires considering also the long-term landfill post-closure condition when the lining system's geosynthetic components may have lost their functionality. Such a new perspective makes many traditional design methods inapplicable. For instance, transit time or breakthrough design methods, which require a contaminant concentration lower than a given threshold value to be reached at the exit of the lining system and at the end of the post-closure monitoring period, cannot be adopted, as they predict an unacceptable condition in the long term. That is the condition of a contaminant concentration higher than the threshold value, without posing the problem of how the future generations will manage that theoretical threat for the groundwater quality. An alternative method is to adopt the performance criterion that the risk for human health and environment remain less than an acceptable threshold level at the point of compliance, not only during the prescribed post-closure monitoring period, but also in the long term. The risk for human health is typically determined by the ingestion of groundwater or inhalation of vapors coming from the groundwater and can be related to a corresponding contaminant concentration in the groundwater through a toxicological model. The risk for the environment is similarly related to protective threshold values of the contaminant concentration in the groundwater, which are typically defined by the regulation in force. As a result, the assessment of the risk requires a contaminant transport analysis to be conducted for the calculation of the contaminant concentration at the point of compliance. In the case of a landfill scenario, the analysis requires identifying a source, that is the waste leachate, a migration path, and the point of compliance. The migration path consists of a vertical transport through the lining system and the underlying attenuation layer, and an advection-dominated transport that occurs within the aquifer, predominantly in the horizontal direction. These concepts are beginning to be included in the environmental regulation of various countries. For instance, in 2020, the requirement to carry out a risk assessment analysis was introduced in the Italian regulations for landfills, the so-called Decreto Legislativo 36 del 2003, for the following cases: when local authorities must authorize particular subcategories of landfills, when requesting a derogation from the permissible concentration limit values in the waste leachate for landfills of non-hazardous waste, and at the end of the post-closure monitoring period, whose duration is typically assumed to be 30 years after the end of the waste disposal activities. Now, several modeling approaches can be adopted to analyze the contaminant migration process in the context of a risk assessment procedure. A first classification of possible modeling approaches may distinguish between steady state and transient models. Transient models take into account the finite mass of the source and time-dependent phenomena, such as radioactive decay, biological degradation, sorption, desorption, and ion exchange. They are computationally demanding and require several chemical, physical, and biological data. In these models, the source concentration typically decreases over time, and the concentration at the point of compliance increases to a peak value, after which it undergoes a progressive reduction in time. On the other hand, steady-state models assume a constant concentration in the waste leachate and typically result in conservative predictions of the groundwater contaminant concentration. These models are attractive as they involve a limited number of parameters and computationally are less demanding than transient models. I want to stress that because of the involved simplifying assumption, steady-state models should not be considered as realistic simulations of contaminant migrations, but as conservative estimates of the risk related to a given contaminant concentration in the source. This concentration in the source can be selected to represent the required scenario, such as the monitoring post-closure period or the long-term condition in which the geomembrane has lost its functionality. Now, I would like to describe a set of analytical and numerical solutions to contaminant transport from landfill that have been developed to assess the risk for human health and environment. This solution has been derived from a steady-state model that has been developed for the analysis of the migration process from a landfill up to a compliance point represented by a monitoring well located in the underlying aquifer just downstream from the landfill. In this approach, the contaminant concentration in the waste leachate inside the landfill is assumed to be constant and equal to C0. The transport through the barrier system is split into two contributions: an advective diffusive flux that occurs through the geomembrane defects, and a diffusive flux through the intact geomembrane. The latter flux component is only of relevance for volatile organic compounds that are able to diffuse through polymeric sheets. The vertical contaminant flux through the barrier system, given by these two contributions, is expressed through an analytical solution, which can be imposed as the top boundary condition for the contaminant mass balance in the underlying aquifer. The contaminant concentration in the aquifer can be obtained in the most general case from a finite difference numerical solution. I will now describe the most significant step of the proposed method. The first step consists of calculating the flux through the geomembrane defects. Defects in the geomembrane can range in size from pinholes to defective seams between geomembrane panels. Modeling assumptions include perfect or imperfect contact conditions between the geomembrane and the underlying soil. For all the possible models, the contaminant flow rate decreases moving away from the geomembrane defect, as shown in the figure on the left. In the proposed approach, an equivalent one-dimensional contaminant flux through the underlying mineral barrier is supposed to take place over a fraction of the total barrier area. This area fraction depends on the number, shape, and size of geomembrane defects and the quality of the contact conditions between the geomembrane and the underlying soil. The second step consists of calculating the diffusive flux through the intact geomembrane. This transport process is relevant only for volatile organic compounds, which can partition into the geomembrane polymer and diffuse through the geomembrane relatively rapidly due to the limited geomembrane thickness. The steady-state flux through the intact geomembrane is assumed to take place over the area fraction that is complementary to the area fraction evaluated for the transport through geomembrane defects. When the vertical contaminant transport through the barrier system has been evaluated, the contaminant concentration in the underlying aquifer can be derived from a mass balance. If the thickness of the aquifer is no more than a few meters, the pollutant concentration can be assumed to be invariant with the vertical position and to depend only on the horizontal distance below the landfill. Under steady-state conditions, the analytical solution that is shown in this slide can be derived. In this equation, RC is the relative concentration, C0 is the contaminant concentration in the leachate waste, CX0 is the contaminant concentration in the groundwater upstream from the landfill, eta is the relation between the horizontal and vertical flow rate within the aquifer, and kappa is a parameter depending on the advective and diffusive transport properties of the barrier system. When the thickness of the aquifer is not limited to a few meters, the variation in pollutant concentration in the vertical direction becomes significant, and a two-dimensional geometry needs to be taken into account. In this case, the contaminant concentration distribution depends on the transversal dispersivity within the aquifer. A general solution can be found using the finite difference method by imposing the continuity of contaminant concentration and flux between the bottom of the barrier system and the top of the aquifer. However, the approximate analytical solution shown in this slide can be derived for the special case of confined semi-infinite aquifers in which the groundwater velocity in the vertical direction is less than 1% of the groundwater velocity in the horizontal direction. I would like now to present an example of the application of the proposed solutions. This example shows how the derived steady-state solutions can be employed to assess the risk for the following two scenarios. The monitoring post-closure period, which is typically assumed to end 30 years after the termination of the waste disposal activities, and a long-term condition in which the geomembrane has lost its functionality. The artificial lining system, in accordance with Italian regulations for landfills of non-hazardous waste, includes from the top a 0.5 meter thick drainage layer, a 2.5 millimeter thick geomembrane in HDPE, a 1 meter thick compacted clay liner, which represent, using the terminology of the European Directive 31 of 1999, the so-called artificial mineral barrier, and another 1 meter thick compacted clay liner that represent the so-called artificial completion of the geological barrier. Below the lining system, a 3 meter thick layer of silt is assumed to separate the artificial lining system from a 25 meter thick confined aquifer whose piezometric level is 1 meter above the top of the aquifer. The temperature at the base of the landfill is assumed to be about 20 degrees Celsius. Therefore, the geomembrane service life is expected to last about 120 years based on the indications given by Rove and Brackman. As a result, during the monitoring post-closure period, the migration of inorganic contaminants consists only of the advective diffusive transport through the geomembrane defects. However, organic contaminants can diffuse through the intact geomembrane with a consequent relevant increment in the overall contaminant mass flux passing through the lining system and reaching the underlying aquifer. The proposed analysis is performed for both cadmium and benzene to appreciate the different behavior of inorganic and organic compounds. The derived analytical solution for thin aquifers can be used to assess the variation of the contaminant concentration in the aquifer along the direction of the groundwater flow. The calculated values of relative concentration for cadmium and benzene in the aquifer are shown as a function of the horizontal distance below the landfill, whose total length is assumed to be equal to 200 meters. Assuming the presence of microholes, holes, and tears with the areas and frequencies shown in the table at the top of the slide, the concentration profiles for cadmium and benzene are similar. Considering a better performing composite barrier with only 2.5 holes per hectare, the relative concentration of benzene is found to be appreciably higher than the relative concentration of cadmium due to the capability of benzene to diffuse through the geomembrane. The maximum relative concentration is found at the exit from the landfill footprint that typically represents the point of compliance for the risk assessment. The procedure allows the admissible concentration of contaminant in the waste leachate to be assessed. This admissible concentration in the waste leachate is given by the relation between the threshold concentration in the groundwater, given for instance by the regulation in force, and the calculated relative concentration at the point of compliance. Using the value of 5 micrograms per liter for the threshold concentration in the groundwater given by the Italian regulations, the admissible concentration for cadmium is found to be 1,786 micrograms per liter. Similarly, assuming a threshold concentration in the groundwater of 1 microgram per liter for benzene, the admissible concentration in the waste leachate is found to be 345 micrograms per liter. If the vertical distribution of the contaminant needs to be taken into account, the solution for thick aquifers can be used. In this case, the contaminant concentration in the aquifer depends not only on the horizontal flushing resulting from the groundwater flow, but also on the vertical dispersion. The contaminant concentration decreases with depth and increases over the horizontal distance. The admissible concentration is significantly reduced by about 50% with respect to the case of thin aquifers if it is calculated as a function of the maximum relative concentration that is reached at the top of the aquifer and at the exit of the landfill footprint. The second considered scenario is that in the long term, when the geomembrane is degraded and has lost its functionality. Under such conditions, the performance of the lining system is significantly reduced. Moreover, as a consequence of the decline of cover efficiency, a mound of the leachate level in the landfill must be expected. The height of the leachate above the bottom line depends on the water balance in the waste body, and in this numerical example, a height of 10 meters has been assumed to have been found from this balance. Because of biodegradation, the concentration of organic contaminants is expected to drop substantially. Attention is therefore focused only on the migration of inorganic contaminants, such as cadmium. Using the solution for thick aquifer, the maximum relative concentration is found to be equal to 0.059 at the exit from the landfill footprint. The corresponding admissible concentration in the waste leachate is 85 micrograms per liter, which is a value considerably lower than the value of 1,786 micrograms per liter found for the post-monitoring condition. And a still more conservative solution is obtained if the admissible concentration is calculated as a function of the maximum relative concentration that is given by the solution for thick aquifers. In this case, the admissible concentration in the waste leachate is found to be equal to 42 micrograms per liter, which is about 50% of the concentration obtained from the solution for thin aquifers. In conclusion, I would like to provide some final comments. This presentation has been focused on a proposed risk assessment procedure that is coherent with the ethical requirement of sustainability in taking care of the impact of our current activities on the quality of the environment for future generations. The ratio of the procedure consists of determining the contaminant concentration in the leachate that are compatible with an acceptable risk level in the exposed groundwater resource, also considering the long-term conditions. However, a last critical consideration should be made about the threshold concentration that are established to preserve the quality of the groundwater, especially when their values are not related to actual risk for human health, but are defined as screening values based on the so-called precautionary principle. It should be taken into account that the threshold concentration we adopt also constitute an ethical choice. For instance, it has been estimated that the limits adopted in radiation protection in Western countries entail a cost of up to $2.5 billion for each hypothetical human life saved. This cost is to be compared with the approximately $100 needed to save a human life in developing countries from infectious disease and other more widespread pathologies. Climate change, the COVID-19 pandemic, and more recently the serious military conflicts that are blooding the world require a reflection on the criteria we adopt for protecting human health and the environment. In fact, awareness has emerged that our health and environmental safety do not depend only on local conditions, but on processes that develop on a global scale. Therefore, we must be aware of the need to make choices that are both economically and ethically sustainable in the face of the inequalities between the various countries of the world and the limited resources available. The sustainability perspective cannot be limited to local assessments, but should take into account the global implications of our actions. From this perspective, the progressive abandonment of the precautionary principle, understood as a criterion of extreme caution in the absence of scientific-based assessment, is desirable. The advancement of knowledge allows us to establish rational criteria for protecting human health and the environment based on specific technical and scientific knowledge. Now, the proposed approach of a performance-based design for landfill lining system is meant to represent a little contribution in this direction. That is the application of scientific knowledge to guarantee the required performances, avoiding the useless and detrimental economic and environmental costs that are frequently involved in the prescriptive-based design founded on the so-called precautionary principle. Thank you very much for your attention.
Can they hear? Yeah, okay. Thank you, Andrea. And it's my pleasure to introduce Professor Katarzyna Zabriela Admeska. Very difficult to pronounce, I'm sorry. She is a full professor at University of Białystok, Poland. And her hobbies are opera and anthropols. She is going to talk about compacted soils, very difficult topic, anthropogenic soils, and when they are compacted, what really happens to them and the intricacies associated with them. She has 2 books to her credit, 110 research papers. She is the president of Polish Committee on Geotechnical Engineering, TC member of Transportation Geotechnics, and she loves to do most of the research in the materials which are new materials. With this introduction, Professor Admeska, please go ahead with your presentation. Thank you.
Thank you very much for your presentation. Dear Chairman, ladies and gentlemen, thanks to organizing committee, I have and especially Professor Eugeniusz Koda, I have a privilege to give a lecture whose aim is to describe selected problems relating to the geotechnical application of industrial byproducts and waste material. Thank you, Professor Koda. We should start from the definition. They are known for most of us, but I should recall them. According to the directive of the European Parliament and of the Council on Waste, waste means any substances or object which the holder discards or intends or is required to discard. The directive also formulates a byproduct, meaning as it is a substance or object resulting from a production process, the primary aim of which is not the production of that item, but may be regarded as not being a waste, but as being a byproduct. End of the waste status take place if the 4 conditions listed in the slide are met. It is not very difficult to fill these requirements. One of them is that substance fulfills the technical requirements for the specific purposes and meets the existing legislation and standard applicable to products. We know that in many countries we have these requirements. The directive also reports possible categories of waste, of which end of the waste specification and criteria should be developed are, inter alia, construction and demolition waste, some ashes and slags, scrap metals, aggregates, tires, textiles, compost, waste paper and glass. Commission is preparing a set of end of waste criteria for priority waste stream, but unfortunately only for iron, steel, aluminium and copper scraps and glass cullet, so for weights that have been accumulated in very small quantities. After this introduction, let's take a look at the situation in Polish landfills. The main 4 groups of non-hazardous waste accumulated in Polish landfills up to 2022 year, excluding municipal waste, are waste from enrichment by flotation of ores and of non-metalliferous minerals. I will use the catalog names, waste catalog names. Tailings and other waste from washing and cleaning of minerals, waste from power station and other combustion plants, and waste from minerals non-metalliferous excavation. You can see the numbers of million tons which are accumulated only in Poland. In figure, we can see generation and storage of this main group of industry weights only in 2022 in 1,000 tons per year. And we can see problems with management of current production in the case of all types of weights, maybe the lowest for tilings. Oh, okay. It was sleeping. Maybe the lowest in the case of this type of waste. So it is waste from washing and cleaning of minerals. The next figure shows us the generation on the left and storage on the right on the main groups of waste in 1,000 tons per year. And we can see that problems of waste utilization has not changed over the years, even after UE directive came into force, and it was not changed after 2020, when it was a border for a better application. Other group of waste that will be described during my presentation, they are accumulated in much smaller quantities, and they are waste material and elements of construction and road infrastructure, and slag from smelting processes, from blast furnaces and steel plants. These waste have many possibilities of utilization, and we should know that waste generation from construction industry constantly increase. In highly developed countries, construction waste constitutes over 17% of the total amount of waste from business activities and households. My presentation aim is to present the properties of non-hazardous industrial byproducts and waste materials and the possibility of their use in geotechnical application. And I will focus on the four groups earlier mentioned, and each of material will be characterized in minerals, graining, and other properties. So we start from coal mining waste, and you should know that coal mining waste, it is a very large group, consists of several catalog numbers and waste. The mineral composition is clay minerals, mainly kaolinite with smaller amounts of illite and chloride, quartz and carbonate substances. Polish coal waste consists mainly of oxides, and this content is given on slides. Waste granulation depends mainly on waste generation technology. Waste from preparatory works and exploitation of gang is characterized by coarse grain size up to 400 millimeters. Other is more fine waste from coal enrichment process is divided in coarse washing waste, fine washing waste from jigsaw, and very fine post-flotation waste. The grain size in landfills is mainly rubble and gravel, changing to gravel, gravel and sand mix as it wetters. And wettering is a main problem. It is especially visible in the case of clay stone, which is given by 1, 3, 6, and 8 numbers. You can see in natural state and after over 9 months of wettering. Lack of resistance to wettering may cause the waste to lose its strength. And I would like to summarize advantages and disadvantages of this waste. Due to the wide grain size range, they show a large dispersion in the values of geotechnical parameters. Most of them is well granulated and well compacted with high values of the strength parameters. The exception is waste with predominance of sandstone. The disadvantages of coal waste is lack of resistance to watering, loss of load-bearing capacity after irrigation of the waste, and the possibility of spontaneous combustion. The next is waste from flotation enrichment of non-ferrous metal ores. It is specific Polish waste because we have the enormous amount of this waste, and the largest in Europe landfill built of this waste, and petrographic composition of post-copper waste from the copper district in Poland consists mainly of sandstone, dolomites, calcite and shales, and mineral composition is silica, carbonate minerals and clay minerals. The main problem is content of copper, because it is about 20 times greater than in soil used for agriculture, but I would like to point the content of lime in the waste. The technology of crushing the excavated materials and the method of transporting and depositing waste is the most significant impact on the grain size of the waste, and they are characterized by grain size ranging from fine sand to silty clays with high plasticity, and geotechnical properties are close depend on the grain size and petrographic composition. The main advantages is the high content of carbonate minerals, which practically eliminates the transfer of heavy metal into solution, but disadvantages is a high content of heavy metals, especially copper. The next is my favorite, fly ash and bottom ash, because I spent whole my life on research on fly ash. Fly ash is primarily composed of glass, carbon, quartz, mullite, magnetite, hematite, clay minerals, feldspar, and lime. And we should know that ashes from combustion of lignite or subbituminous coal are characterized by a high calcium oxide content of about 25%, and this weight has self-cementing properties. Waste come from combustion of anthracite and bituminous coal, contain less than 7% of lime, and exhibits pozzolanic activity requiring a cementing agent. The grain size is different. It depends on the kind of waste. So fly ash corresponds to silt. Bottom ash in the natural states corresponds from medium sand to gravel or sand and gravel mix. But fly ash and bottom ash mixture depends, the graining depends on the technology of storage and kind of landfill. It is landfill or it is a wet reservoir. You can see that fly ash and bottom ash have many advantages, and as binding and pozzolanic properties, significant variability in grain size due to compaction or frost, lightness of the material, large angle of internal friction, and high CBR values that increase over time. Waste which is embedded in the earth structure swells only in the absence of total load. They have a load permeability and water absorption, but it can be advantages or disadvantages. It depends on the application. Disadvantages is low resistance to erosion, and we came back to the hydraulic conductivity and absorption, because if this waste is not very well compacted, it may be a problem in the future in strength. The next is a slag from smelting processes, and the exemplary blast furnace slag from one of the Polish steelworks. Its content is given on the slide. The content of steel slag is quite different, and you can see it below. Slag with lower content of free lime have pozzolanic properties, but high content of free lime allows to use of slag as a hydraulic binder. The grain size of blast furnace slags corresponds to the grain size of stony soils, rubble, and weathered material. Waste from existing metallurgical heaps is characterized by high variability in granulometric composition. It depends on the type of the waste which was disposed, but nowadays this type of waste are disposed separately. Advantages is high compressive strength, high angle of internal friction, and low water absorption. Fresh slags are subject to a disintegration process and volumetric stabilization of the material, and slag have high compressibility and sensitive to moisture. The last group is construction and demolition waste. Waste contains sorted grains bound with hardened cement slurry, which consists mainly of hydrated calcium silicate, and waste from road elements may contain chlorides and sulfates from diesel oil and engine oil. Aggregate made from crushed concrete is characterized by sharp aged grains and roughness of the surface mortar adhering to the aggregates. In the table, we have a composition of the construction rubble in percent, and we can see that brick and concrete are the main waste in this group. Advantages is very good CBR load-bearing capacity and great angle of internal friction. Disadvantages is that it's a heterogeneous material. Water absorption is 10 times higher than the indicated in the case of limestone aggregate. Frost heave and water absorption limit the use of concrete rubble for incorporation above the groundwater table and below the impact of frost, and use of gypsum waste should be limited too. My next slides are focus to possibility of their use, taking into account the properties which were described, and the main volume of this presentation will be concerned construction of the embankments and construction of sealing layers. So we start from embankments and from coal mining waste. And as I said earlier, most of the coal mining waste are well compacted, and they are good material for the construction of road embankments, and table presents the criteria for the use coal waste for road embankments for the bottom and upper layers. Coal waste incorporated into embankments has a risk of spontaneous combustion when the content of the flammable parts exceed 30%, and in highway embankments the organic content should be limited to the 20%. The next is the criteria using fly ash and bottom ash mix to the embankment. And I would like to say that already in 1981, the Polish Road and Bridge Research Institute gave guidelines regarding the incorporation of the compaction with specific properties. And beneath a red line, we have properties which are additional requirement. We should know that fly ash bottom ash mix should be isolated from grey water. So you can see at the figure A that directly they can be constructed only in dry areas. When we have wet areas with high groundwater level, we should have a cut-off layer or use geomembrane. In flood areas, cut of layer should be given too. While forming embankments, the most important thing is the appropriate compaction of the waste. Dynamic compaction destroys waste grains, and crushed spherical grains with larger dimension are filled with smaller grains, which improves their packing without the need to increase the moisture content. So you can see on this figure the next compaction of the same sample. That's why a laboratory determination of compaction parameters on repeatedly tamped samples leads to the incorrect assessment of the compaction effects. The values of CBR of fly ash bottom ash mix are usually much higher than those obtained for minerals soil corresponding to their grain size. And these properties strictly is connected with water, optimum water content. We can see it for 3 different sample of the waste. The next is slag from smelting processes. I said earlier that we have a problem with irrigation of this material too. So they should be incorporated in the same way as fly ash, because saturation of the sample with water may cause a 50% decrease in the value of internal friction angle. So we should, on flood areas, we should give the cut-off layer too and incorporated material above the level of flood. The next is waste from flotation enrichment. Because of the high content of heavy minerals in the waste, nearly 65% of this waste is used to build embankments of the Żelazny Most, which is tailing pond, and seal the bottom of the reservoir. Depends on the graining of the waste. Construction industry waste can be used both into the load burning layers and the foundation, and for concrete mixture. but construction rubble containing ceramic waste, concrete mortars, soil, etc. Can be used only for build the body of road surface and prepare the ground of the construction of the road. Materials incorporated into embankment structure should have a frost heave lower than 50 millimeters, defined as the maximum increase in height of the sample in 96 hours. Material that does not meet the condition should not be installed within 45 centimeters of the surface. On this slide, we have categories of concrete following the French recommendation, and after this French recommendation, we have 5 different aggregate categories related to different use as backfill material, or road base, or groups 2, 3, and 4. They can be used as mechanically and chemically stabilized construction. Some words about construction of ceiling lawyers, as the ceiling lawyers can be used waste materials with very fine graining. It may be wetted gun, but in water environment, post-flotation waste from hard coal, fine-grained carbonate waste from flotation enrichment, and non-ferrous metal ores, and obviously fly ash. Fly ash can have a proper hydraulic conductivity to construct lining beneath the landfill. And last, improvement of the ground, and only 2 slides for improvement of the ground are used blast furnace slag burned by a shell, mining stone, and crushed building materials, and fly ash is used as a substitute for cement, and slag as a filler where performing a subgrade reinforcement using soil fracturing. And in case of compaction grounding, fly ash can replace more than 50% of cement. Fly ash and slags from smelting processes are used for construction of DSM columns, and we can see the Keller Poland photo with this structure. And conclusion, the first of them is general. I would like to read the second and third. The second is anthropogenic soil is a valuable waste material with many possible uses, and geotechnical parameters of waste incorporated into our structure often exceeded the values obtained for mineral soil correspondent to their grain size. And preparation of the set of the end of the waste criteria for priority non-hazardous industrial waste streams should be accelerated, especially since the technical requirements for geotechnical application have been known for many years. Thank you very much for attention.
Thank you very much, Professor Katrina. And we had 3 good presentations, excellent presentations by Krishna on biochar, Andrea on contaminant transport, and on anthropogenic materials and their utilization for modern day construction by Katarzyna. So thank you very much for being with us, and over to Magdalena now. Or I think, Pietro, you would like to say something?
I would like to ask our distinguished guests to remind, or maybe come up to the stage for the group photo and for the souvenirs, because you fully deserved appreciation of the effort you put in such a wonderful keynote lectures. I think we all agree on that. Thank you. Ladies and gentlemen, just a few more announcements. It's the lunch break right now. The lunch break is going to be held at the Water Center, the place where the welcome reception was held last night. For those who are not aware, where is it? You just need to exit the main hall, turn left, and follow the arrows with the Water Center on it. Just turn left, it's across the street, and then follow the left side. For the evening, there is a gala dinner that's going to be held in this place, and our guests who are accommodated at the Arch Hotel, there's going to be a bus to pick you up to the gala dinner, and the gala dinner is going to be held here in this hall. All right, so enjoy the rest of the sessions, and I'll get back to you very soon. Thank you.